The start because then the element is actually analyze the next lecture. So like we will like really adamant about must be on fire and the doors. Then yeah, since there's one more motivating to start and then for the recording, I guess it's already in order.
I think it is recording. Yeah, I did get some. Yeah.
All right, so welcome everyone. So it's my great pleasure to introduce Prashant Doshi. So Prashant is a professor at the University of Georgia in Athens. And so he's visiting us for the entire week. And in fact, we had the privilege to have him come and visit several years ago for his sabbatical. And that has led to some very good collaborations. And he's back visiting us again. And so there's an opportunity for anyone interested, in fact, to meet with Prashant, start some collaborations. So I would highly encourage it. So Prashant is an expert in multi-agent systems. So in fact, he pioneered some of the work about interactive COM-DPs. And today, he is one of the leaders when it comes to decentralized planning, whether it's partially observable systems or, I guess, multi-agent systems in general. And I guess he will tell us about some of this work today. And that encompasses a wide range of applications from robotics to other industrial projects that he may touch upon in his talk. All right, so let's welcome Prashant.
Right. So my name is Prashant Doshi, and I'm a professor of computer science at the University of Georgia. That's about 90 minutes northeast of Atlanta. So I welcome you to visit the university if you happen to be in Atlanta. I've also been directing the Think Lab at UGA. And at the lab, we do a number of different projects related from robotics all the way to multi-agent planning and multi-agent reinforcement learning. So we do have a really wide variety of projects, but you know, Okay. So the underlying theme, you know, for most of the projects in my lab is multi-agent systems. All right. So if you're interested, you know, in anything related to multi-agent systems, I would be really happy to talk with you. And I'm here until Friday evening. So, you know, feel free. And also, you know, we can always chat once I get back as well. So the work that I'm presenting today is on multi-agent reinforcement learning. And this is joint work with my doctoral student who recently graduated, Kayam A, and Professor Bikramjit Banerjee from University of Southern Mississippi. So this work is going to be on a relatively new paradigm for doing reinforcement learning in multi-agent systems that is based on decentralized training and decentralized execution, right? So with that, I'm going to go straight into the talk. So here's the outline. So I'm going to start by giving you sort of a brief introduction to multi-agent reinforcement learning, especially, you know, what are some of the challenges in MARL, because I understand that many of you all are working in single agent reinforcement learning. So the multi-agent world is, you know, take it from me, it's a lot more exciting than single agent. Okay. Next, I'm going to introduce a new domain that involves co-opetition. If you haven't come across this term, it's okay. I hadn't either until I talked with some business school folks, and they told me that a mixed motive, cooperative, competitive setting is also called co-opetition. So basically, this is cooperative, competitive setting. All right. Then I'm going to talk about a new reinforcement learning technique in multi-agent systems that basically allows agents to do reinforcement learning under co-opetition. And finally, you know, just quickly browse through some experiments and, you know, tell you all some important conclusions and takeaway messages. Okay. Now, you know, we can structure this talk so that in a way that if you'll have any clarification questions, feel free to ask. I have planned this talk for about 45 minutes. So I think I do have, you know, I will keep some time at the end for Q&A as well. But if you all want to ask questions during the talk, that's perfectly okay. Right? So no worries. Okay, so with that, let's get started with reinforcement, multi-agent reinforcement learning challenges. Okay, so here's the general RL loop, right, for single agent reinforcement learning. I'm sure that many of you all have already seen this before. Many of you all have actually looked into this deeply, so I'm not going to spend time on this. But screen is sharing. Can you?
So, yeah, we're still on.
Okay, all right. So I'll just share it again. All right. Okay, no worries. So I'm just going to share my screen again, and I think this should work. No, this one. Okay. How about now?
Yeah.
All right, perfect. Okay, thanks for letting me know. Okay, all right. So this is the single agent RL loop. I don't want to spend too much time on this because I would much rather spend time on the okay, something has happened. It's not progressing. Okay, I would much rather spend time on the multi-agent RL loop, which, as I told you, is a more exciting world for me. So it's similar to the single agent RL loop. The only difference is that you have n agents, and then every agent's action contributes to the environment. Okay, so every agent's actions impacts the state of the environment, and then the environment responds with the state and the reward signals for the agents. Now, the key here is the reward signals. So in cooperative settings, every agent sort of gets the same reward signal. But in competitive settings, each agent may get a different reward signal. All right, so the reward signals really, determine the type of setting that you're inhabiting. Other than that, is similar to the single agent RL loop, just the presence of multiple agents. All right, so in the past few years, there has been a lot of excitement behind reinforcement learning, which is why there are so many students and even industry researchers interested in reinforcement learning. So the excitement began with some amazing advances by companies like DeepMind in board games like Go and chess. You have AlphaGo and Alpha Chess, I don't know, something like that. But you may not know that reinforcement learning is also being used in recommendation systems. So for example, it is being used by Netflix. It is also being used for online shopping. There are so many applications of reinforcement learning on Shopify and so on. Amazon is looking into reinforcement learning as well, not only for improving your shopping experience, but also for detecting fraud, for example. So reinforcement learning is really pervading a lot. And, we may feel like the environments generally are perfectly observed, especially if you just look at games. And in the case of games, yes, they are, because you normally can see the entire board position. But if you really go to the physical world, then oftentimes these environments lack perfect observability. Okay? And so then the question comes that, okay, then how do you model partial observability? And in my work, I normally model partial observability in two ways. So first is, what is partially observable, right? So the state is partially observed. And in the multi-agent setting, the other agent's actions are also partially observed. Okay, you may not perfectly observe the other agent's actions. So when it comes to state, we generally model the observability by saying that the state is observed using public observations, whereas the private action, the actions of the other agent are inferred using private observations. So a public observation is one that is common to all agents in the setting, because generally the state is common to all the agents, whereas a private observation is private to every agent. Okay, so that's the distinction that I make in terms of observability of the state and the action. All right. So in other words, this is the sort of the schematic for our agent. Okay, so we have the environment, we have the other agents, the agent here receives a public observation and a private observation. The public observation gives it information about the state of the world, and the private observation gives it information about the other agent's actions. Okay, and it may receive these noisily. So there's a noise model or a sensor model attached, to those observations. Just like, so think of it as your agent being a robot. Now, when it comes to this setup, then in the context of partial observability, your optimal behavior may also require information gathering actions, which is not the case in contexts involving perfect observability, right? You don't need to do anything explicit if you assume that you know the world. But when you assume that you do not know the world, then your actions may also involve information gathering actions, okay, where you need to go to some place to get more information. Okay, so that's a difference, between perfect observability and partial observability. Okay, now in multi-agent environments also introduce, many new challenges, and I just want to quickly walk through some of these challenges. So the presence of other agents basically makes your environment non-stationary. What does that mean? You may have actually heard about this many times, right? That the multi-agent setting, the environment is non-stationary. So basically what that means is that the environment transition no longer depends on just your action, but it can also depend on the other agent's action. So while you may be performing the same action, but because the other agent performed a different action, the transition, the environment transitions to a state that you did not anticipate based on your own action. Okay, so that's why the environment is non-stationary. So how do you deal with this? Well, one way of dealing with this is to simply assume that you know the other agent's actions. Okay, you can perfectly observe the other agent's actions. Another way of dealing with it is to try and infer the other agent's actions. Okay, so think of your agent as this one in the middle here. So this one. So this agent is tasked with doing reinforcement learning in a multi-agent world. And it either observes the other agent's actions or it estimates the other agent's actions. So here, this agent is basically maintaining estimations of the other agent's behaviors. And maybe these estimations are in terms of models. So now you can actually use Bayesian inference to try and update your estimation of the other agent. Okay, so Bayesian inference also plays a really important role in multi-agent settings. All right. Another challenge in multi-agent settings are the types of different environments. So like I said before, we have cooperative environments, we have competitive environments, and then we also have mixed motive or cooperative competitive environments. So in terms of cooperative environments, the general understanding is that all the agents share information with each other and there is a common goal. Okay, it's like think of a team. There is a common goal. In competitive environments, there is often hidden information. You may not be able to observe the other agent's actions. I mean, he's not going to tell you what he's doing, right? In competitive environments, there is no incentive for him to reveal that normally. And the games, can range from being loosely competitive to being strictly competitive. So they can also be zero-sum games, right? Whereas in mixed motive, cooperative competitive settings, normally the agents have a fixed or a dynamic relationship. So think of a team of agents who is competing with another team of agents. Okay. And normally the way you model the rewards or the payoff structure is similar to a general sum game. Okay, so here we have a team of agents. So they're all cooperating amongst each other, but then they need to compete with another team. So you can see that there is cooperation as well as competition. Okay. All right. Next, I also wanted to touch upon a little bit, not too much time, but on the different learning paradigms in multi-agent reinforcement. So the most common one so far, if you go through the literature, the most common one so far is something called centralized training, decentralized execution. So here the idea is that you have a centralized controller that is basically receiving information about the other agents, about all the agents' behaviors. So all the agents are transmitting their behaviors to the controller. The controller basically responds by giving every agent a valuation of the behavior. The valuation can be in terms of the advantage function. And then the agent basically takes that valuation, tries to improve on it, and arrives at its own action. and its action may just depend on its own observation. Okay, so this is centralized training, decentralized execution. Now, the other paradigm, which you may not have heard about a lot, is decentralized training and decentralized execution. So here, every agent has its own controller. And this controller tries to maintain an estimate of the other agent's behavior. So it's not explicitly receiving that information, rather it's trying to infer that information from the environment signals and signals about the other agents. And using that, it arrives at a valuation for every agent's behavior, which again could be the advantage function, passes it on to the agent, and then the agent improves on that to arrive at this action. Okay, so you can think of a decentralized setting is where the agents are kind of loosely coupled. So if you think about it, the incentive for an agent to share its information normally comes in cooperative settings. There is little information, there is little incentive for you to share your information with somebody who is not your well-wisher, right? And so normally this paradigm applies in cooperative settings, but if you start thinking about competitive settings, then it's kind of hard to justify this paradigm. And so you probably need something like this. Okay, and that's really the motivation for this paradigm. All right, now interestingly, there was a recent paper in, I think this was in AMAS, if I'm not mistaken, that actually showed that using the CTDE paradigm, so centralized training, decentralized execution paradigm, you may not learn to coordinate in some games. Okay, so one may think that because you have a centralized controller, you should always be able to pick up on the coordination that's needed. But turns out that if the agents start by assuming that they don't know anything about the other agent and then start receiving the actions of the other agent's behavior, they may actually learn, they may not learn to coordinate in some of these games. So it's an interesting result, but it basically tells you even the limitation of CTD in some settings. Okay, now if you look at the literature in the last few years on multi-agent reinforcement learning, you will see that most of the methods are following the policy gradient approach. Okay, we have two general approaches, right, in reinforcement learning, value-based and policy-based. So most of them are following the policy gradient approach, and they are mainly applying this actor-critic schema here, as you can see. So essentially in this approach, you're trying to learn, directly trying to learn the mapping from the states to actions. And most of these approaches tend to be on policy. So some of the recent algorithms that I'm sure you may have heard about is MADDPG, one of the more popular ones, and then there are more recent ones like COMA and LOLA. There is multi-agent PPO, and then there is a very recent one called local information agent model. Okay, so yeah, this is an exciting world. A new algorithm gets published probably in every new machine learning conference in this world, in the multi-agent reinforcement learning world. So it's a really fast-moving world at this point. All right. Now let's also take a look at some of the domains, right? So all these papers that are getting published, how are they evaluating their methods? So one of the most popular ones is the multi-agent particle environment, which is basically a predator-prey kind of game with obstacles. Okay. Another one, which I'm sure you all have heard, is the StarCraft multi-agent challenge, which I believe is from DeepMind. Okay, so again, this is another domain. And then the third one is Petting Zoo. Petting Zoo is basically a bunch of multiplayer. I think what they've done is they've taken all those Atari games and turned them into multiplayer games. So for example, you have like basketball Pong. Okay, and then you have something like hold on, there's an interesting one. Yeah, foosball. So it's a combination of foosball and Pong. Okay, so it's basically taking all those games and turning them into multiplayer games. So yeah, this is a really interesting test bed as well. Okay, so I'm going to pause here and see if there are any questions. If not, I'm ready to move on to sort of the next part of my talk, which is the new domain that I would like to introduce. So far, I've given you some background on multi-agent reinforcement learning and the challenges. Any questions? Yes. Yeah.
So you need this distinction between the public information and the private information?
So how is it like different from a multi-agent understand? Is it like the public information is available to all the agents? Is it like the same information is
Correct.
available to everyone?
Correct.
And private is different from agent to agent?
Exactly right.
Okay.
That is a distinction I'm making.
So if you. Oh, sorry.
What was that? Oh, do you want me to repeat? Okay, so for the Zoom audience, I'm just going to repeat Sriram's question. His question is the distinction between public and private observations. So yeah, maybe the people who are asking questions can try and ask a bit louder. I don't know how well my microphone works.
Okay, yeah, so just to follow up to that, so the CPD setting, can you tell me like what exactly is public information, what is private? So what is
Okay,
the-
so in the CTDE, everything is public. There is no private.
Okay.
Because the actions are broadcast to everybody, right? There's only a single controller, right? So every agent broadcasts his actions to the, not broadcast, but basically communicates his action to the controller. And, you also know the state of the system. So one would say that, yeah, I think everything is public there.
Okay, and in the DTC or
DTD,
yeah, in the DTD, then the actions of other agents will be private.
exactly right. And primarily because, agent one is performing some action, agent two is performing a different action. So from your perspective, you just need to, understand what action the agent two is performing, whereas agent two is trying to understand what action agent one is performing. So the signals that they're receiving are different, and each one may have a different sensor model as well. So I'm glad you picked up on that distinction because it is an important distinction.
Units like that,
Where?
where you had the centralization.
Sure.
So
Okay.
I see that these are pi, like pi one to pi next.
Yes.
This represents policy. Can we replace that with actions, like something
Yes.
like thoughts are? So instead of going in the entire policy.
You can replace it with actions, yes. So the question is whether in CPDE, can you replace the policies with actions that are shared with the controller? Yeah, you don't need to share your entire policy. You can just share your action at every step as well.
Do you use any optionality?
I don't think so. I don't think so. I don't think I need to know your entire policy from before. In fact, that may not actually work because your policy is evolving. So as long as you are transmitting your action to the controller perfectly, I think you can, well, okay, so the optimality question is a bit different, but in terms of equivalence, I think it's the same. Now, in terms of optimality, I think this result is interesting. Okay, so basically this result shows that you may not converge to coordination or cooperation that is needed in that domain. And so if you look at this paper, there are at least a couple of games where they show that this is not happening.
Obviously, having actions rather than policies is a lot cheaper to implement.
Yes.
And
Correct.
then all of these, as you mentioned, are on policy.
Yes. Most of them are on policy. Yes, correct. It's sending the actions back, actually. Yeah, it's not sending the policy. I mean, I think there's a risk in sending your policy, especially if your policy is evolving. So it's better to just send the actions back.
But I think that most of these at least model the centralized control that could model everybody's policy.
Yeah.
Evaluating the value.
So the way the methods differ is basically what kind of a representation they're holding for the other agents in the centralized control. Yeah. Okay. Any other quick questions? All right, great. So so I'm going to move on to the next part of my talk, which is the org domain. Okay, so, so basically we introduced a new domain called the organization. Essentially, our inspiration is to model a business organization where employees are facing a mixed, cooperative, competitive setting. If you think of yourself, we are in an academic setting, so I don't know what our incentives are. We have different kinds of incentives than employees in a private organization, but nonetheless, I feel like every employee in any organization, faces a conflict between acting for himself or herself versus trying to do the best for the whole institution. right? And so if you think about it, employees in an organization are basically facing a cooperative competitive setting or something called as co-opetition. So in this domain, we have partial observability very naturally. We have a non-Markovian reward. I will touch upon that. The domain scales very naturally because organizations can be really small to being really large. There are substructures in organizations. There are units and there are groups and so on. And also, an organization tends to be an open agent system. So in contrast to closed walls, an open agent system is one where agents may enter and leave at any time. And that's certainly true in an organization because employees always have the freedom to resign for other opportunities, right? Or they have the freedom to move from one group to another. So this domain actually models a lot of different interesting characteristics that one would want in a multi-agent. Okay, and it's really come out of some discussions with faculty in management science and organizational psychology. All right, so let me tell you a little bit about how we are modeling this domain computationally. So every employee has one of four actions. So let me just tell you it's a discrete domain. Okay, it's not a continuous domain, it's a discrete domain. So every employee has one of four actions: self, balance, group, and resign. Self here means that the action is mainly for the benefit of the employee herself. Group is where the action is for the benefit of the entire organization. Balance is where you are basically balancing between doing something for yourself versus the whole organization. And resign is, what resign is. So in this talk, I'm not going to talk about too much about the openness of the environment, which is why I have resign grayed out. All right, now let's talk about the joint actions. So joint action is basically when all the employees are acting. So again, the joint action is also one of these three: self, balance, and group. Okay, so the joint action of all the employees is self, when the number of agents picking self is greater than the number of agents picking group, and so on for balance and group. Okay, analogously for balance and group. Okay, so even the joint action is just basically self, balance, and right. And the manager has similar actions, except the manager can also hire and fire. But in this particular organization, I'm not going to, at least in this talk, sorry, I'm not going to consider manager's behavior. I'm only going to focus on the employee behaviors. All right, let's talk about states. So the states in this domain represent the organization's financial health level. And so, we modeled it, we tried to keep it simple. So we basically modeled 5 different states, but if you want to use this domain, you're totally free on how many other states you want to model in terms of the financial health level. And if you think about it, most employees do not know exactly the financial health level of the organization they are in, right? For example, the recent layoffs in the high-tech sector is a big example. I have many friends who are working in Google, Amazon, Apple, and none of them predicted, those levels of layoffs. Okay, so most of us don't really know the financial health of the organization that we work in, although we would like to. And how does the state transition? So here's how the state transition happens. If the joint action is self, then the state decreases by 1. So basically, if you just keep on acting for your own benefit, then you're not acting for the benefit of the whole organization. And so the financial, the organization starts doing worse and worse. Okay, that's the idea. Balance, that's great. Group, then the financial health of the organization increases by 1. So basically it becomes better. And then you also have something called group all, where it can increase by 2. Okay? If everybody does group, like all the employees are just working for the benefit of the organization and not really doing anything much for their own welfare or their own growth. All right, let's talk about the reward. So this is where the real fun begins. So every employee basically receives 3 types of rewards. First one is the individual reward, which basically reflects the salary that the employee is getting. It can also reflect, the gratification that the employee receives from working in that organization, and also maybe, the meaning that the employee assigns to his or her work. Then there is a group. So the individual reward depends only on the agent's own action. See that? Then the group reward depends on the agent, on the joint action of all the employees. And this is basically the reward that the organization receives, and we are also modeling a bonus. So in private organizations, normally, the bonus depends on how the organization performed in the previous fiscal year. Okay, your bonus is a reflection of how the organization did in the previous fiscal year. So your bonus tends to be history dependent. And here's how we are modeling the bonus. Okay, so it is some factor, some fraction of the total individual reward. Basically, yeah, so this is the sum of the individual rewards, and this is R0, which is the total reward from the previous step. Okay, so we have three types of rewards, and this is why, this is basically a domain where you have, you're basically facing a choice between how should you act. Should you act just for your own benefit? Should you act for the organization's benefit, and so on. Now, one thing that we do to simplify here is that we assume that the employee's reward can be a sum of all three. Okay, that's not always the case. You cannot always combine these rewards. So that is an assumption that we are making, that we can combine these rewards together. Right, and here's a manager's reward. So again, I've graded out because I'm not going to focus on the manager in this talk, but you can see that it's very similar. His reward is some fraction of the total employee reward, the group reward, the bonus, and then I'm removing a constant C, for reasons which I can discuss with you after the talk. All right, so basically we have this way we are modeling co-opetition. Yes. Well, the reason why okay. So the question is that in RL, why do we need the bonus reward when you're optimizing the cumulative sum of rewards, right? Right. The reason why you still need this is because this is an explicit reward in your reward function. It's not the same as just optimizing the sum of the rewards. So it is an additional signal that you get that actually impacts your performance in different ways. And we actually did an experiment where we showed that modeling bonus does have, it does change the behavior of the agents. So if you don't model the bonus, you get a different behavior. You include the bonus, you get a different. So it is an explicit reward signal that you do need to add in your reward function. The problem is that it is history dependent. Okay. All right. So let's also move to another aspect of this domain that I like, which again comes naturally, and that is organizations tend to have various structures, right? Think about all the different companies that you may have worked with or you may have interacted with. So organizations tend to have different structures. So for example, here are some of the structures that we have modeled in the previously. Again, we're not limited to these structures, but these are some common structures in organizations. So here, directly connected agents are neighbors, and then the group reward. Remember the group reward RG. It is only shared within the neighbors. Okay, so the group reward is calculated on the basis of your neighborhood. All right, so think of it as like a unit reward or your team reward. All right, so takeaways from this domain. We think that it can serve as an important benchmark for cooperative competitive settings. And basically it allows the community a way to start thinking about reinforcement learning in contexts involving co-opetition under partial observability. All right, so much of the work so far has mainly focused on cooperative settings. There is some work on competitive settings, but then, co-opetition is a fairly common setting as well, in the real world. And one example that comes to my mind is really the relationship between Apple and Samsung. So at least a few years ago, Apple was really relying on Samsung to fabricate all its chips. But at the same time, they are heavy competitors in the cellular world. And so they always had to balance, this relationship that they have. So at least in the management science, there is a lot of awareness that there is co-opetition between units in an organization and even between organizations. Secondly, we can represent various types of business organizations. So you can do some macro level modeling of organizations as well. You can run simulations, and all of this can be tied to work under, to research under the future of work. And it can naturally scale to hundreds of agents. We can have 10 employees to hundreds of employees to thousands of employees in an organization. And finally, organization also naturally allows for openness. And this openness arises not just from exogenous events, but also from the agent's own actions. So agents may choose to resign from the organization. Managers may choose to hire and fire. And so your world, the agent's world is no longer closed. Okay. So before I move on to the final part of my talk, any questions on this domain? On the organization domain? Yeah.
So the history component, the reward was that intended to make it non-marketable? Is that why you meant the component?
The bonus?
Yeah. So the reason why you added the bonus was to make the reward non-marketable?
No, that wasn't actually our motivation. Our motivation was to actually model the bonus. Because in many organizations, bonus is a really important part of your compensation. For example, if you take financial organizations, your bonus sometimes exceeds your base pay. So bonus is a really important part of your compensation. And so when I was talking with my collaborators, they said that if you really want to make this realistic, you need to model bonus. And then I realized that, oh, but this makes my rewards non-Markovian. So now what?
Aggregate value of previous performance and all the things that do at the current time.
Correct. So I'm going to tell you how to model this. Right. So you're going into, how to deal with this bonus. Right. Right. Yes. Right. Yeah. So the question is, what is the objective in the organization domain? The objective is for every employee to maximize the combination of those rewards. And if there is a manager involved, then the manager is also trying to optimize its reward. And we are looking at all of them, we are taking the perspective of every employee, but we're also looking at the organization as a whole. All right. Okay. So let me go on to the last part of my talk, which is basically the new method that I would like to introduce. So, so this is a method that is obviously based on the actor-critic schema, as you can see in the name of the method. And our motivation was to really see if we can do multi-agent reinforcement learning in a cooperative, competitive environment under partial observability. So at least, so far in the literature, there isn't a method that just applies readily to this domain. And I'll show you some evidence of whether existing methods can readily be applied, to this domain. Right. So at least we did not find any. The main idea here is to, is for the agent to pursue a fully decentralized approach. And we basically selected the actor-critic schema. And so the agent, pursues a fully decentralized actor-critic schema by predicting the other agent's actions. Okay. So we are going to try and predict the other agent's actions. For every reinforcement learning technique, there is an underlying model, right? For many single agent reinforcement learning techniques, the underlying model is an MVP. So here, the underlying model is a simplified version of the interactive POMDP framework. If you don't know about this framework, it's okay. I'm not going to go into this framework, but just know that there is an underlying model here as well. And so we can lean on that model. Now, so in response to Mark's question here, now the bonus, right? So the bonus is non-Markovian. And the way we try to reclaim the Markov property back in org is basically we add a continuous valued feature called SR. We denote it as SR, which basically memorizes the reward from the last step. So if you're interested in knowing how I do this and then how it changes the model, we have it, we have the details in the paper. I'm not going to address this here because I really want to just focus on the approach, but just know that we have been able to include the bonus and then make the model Markov. Okay. So let me start by giving you a brief overview of this new technique. Okay, so the main idea here is that every agent maintains belief over the other agent's models. And so then the question is, what is a model here? Okay, so a model essentially includes a map from the agent's observation history to its actions. So basically the agent function, or you can think of it as a policy. In addition to that, the model also includes the agent's observation history so far, its policy, and then its private observation model. Because every agent may have its own private observation. Okay, so that's a model that we are using. Again, you're not limited to this model. The approach is generic. It's not specific to the kind of model you want to use. You just have to make sure that the model can allow you to predict the other agent's behavior. Okay, so the way we go about including the prediction is by including a belief filter in the actor-critic schema. So here's your actor-critic schema. Okay, here's the actor, here this whole thing is a critic. So we include a belief filter in the critic. And here I show some details on how the belief filter can be included. I think that it's kind of straightforward, but if you're interested, we can talk a bit more about this architecture as well. Essentially, the belief filter updates the belief over the models of the other agent, and then uses this distribution as a sampling distribution to predict the other agent's action. Okay, so here, so we basically use this belief as a sampling distribution to predict the other. Hold on, I'm going to take questions a little bit at the end because I think I'm running a bit slow. So let me speed up a bit, right? But I'll definitely come to you. All right, so essentially the actor responds with the private observation model. So here's the private observation model, the observations that are coming from the environment. So all that goes onto the critic. Then the critic does its job of doing the belief filtering and so on, and the evaluate, and basically sends the action, the action coming from the actor, so the agent's own action, and the predicted action to the advantage function. And so think of the advantage function as giving you a valuation of the current behavior of the agent. Okay, so see how it uses a predicted action as well. Right? Okay, so what's the limitation? Well, the limitation is standard to many multi-agent learning algorithms, which is that the joint space, the space of joint actions grows exponentially with the number of agents. And we are not able to get past this limitation in what I've shown you so far. So the method that I just showed you still is impacted by this limitation. And this is a really fundamental limitation in multi-agent systems. Okay, it's very similar to the curse of dimensionality. Okay. But if you think about large domains, and here, there's what I'm about to show you is really based on a lot of understanding in the multi-agent planning community that we have gained over the years. Many large domains exhibit two properties which you can really leverage, which is action anonymity and population homogeneity. So action anonymity essentially is based on the fact that in large populations, oftentimes all agents have the same action space, and which agent performed that action is not relevant. Okay, so which agent performed the action is not relevant. Which action was performed is relevant. That's action anonymity. Second one is population homogeneity, where most of the agents in the system are very similar and they're homogeneous, and so the state transition and reward depend on the count of distributions of the actions, not on which agent performed the action. Okay, and this count of distributions of actions is what we will call as a configuration. All right, so these assumptions, very powerful assumptions, they have really been leveraged in the planning community to scale up their decision making to thousands of agents. And we are bringing basically those assumptions from planning onto the reinforcement learning. So let's talk a little bit more about action configuration. So action configuration is a vector of counts of distinct actions that is performed by the agent population. Okay, so an action configuration basically looks something like this. And any joint action can be mapped to a configuration. Okay, and we assume that this is done by a projection function delta. So here's an example. Here's a joint action by 4 employees, and you delta will map it to this configuration. So here, this is for self, balance, and group. So 2 self actions and 2 group actions. So see how it goes from the joint action space to a configuration. Okay. Now, you may have realized that delta is a many-to-one mapping, which basically signifies permutation invariance. So no matter the ordering of these actions, it can be self-group, you still get this. See, so it is permutation invariant. Okay. Well, you have lost something now. And what you have lost is that given a configuration, you cannot get back to the original joint action that led to that configuration. Okay. So this, this use of action configuration is only possible under the assumptions that I told you before. If you don't have those features in your domain, you may not be able to use this action configuration. All right, so moving further, I can now take my transition function, my public observation model, my private observation model, my reward function, and basically take the joint actions of the other agents and replace them with configurations. Okay, so now these functions now become my starting point, right? Where the configuration is just a vector of counts of actions, right? And so the above equivalences, they naturally lead to the same equivalence for the Q function as well. And so a Q function is also now a function of the configuration, and this carries forward to the advantage function also. Okay, so in this way, I have now made it, I've at least inhibited that curse of dimensionality, because I'm no longer impacted by the exponentially growing action space. All right, so here's a belief update with action configuration. So I did not show you a belief update before, how the update happens, but this is how the update happens. It is a bit involved, but here's how you predict the actions of the other agent. Here's the private observation model, and here's how you're keeping track of basically the, the history, the observation history of the other agent. So I don't think you need to spend too much time on this, and at least right now. But here, what I really want to point out is how the configuration appears into the belief. So you can now see that once I have the belief over the models of the other agent, I can use that to arrive at the distribution over configurations. And so obviously you're wondering, well, what is the complexity, how expensive is it to arrive at this distribution over configurations? Turns out that there are well-known ways to do this. This is actually work by Kevin Layton Brown and his student from 2011. So he introduced this concept of action anonymity in the context of single shot games. And basically he has, he presented a dynamic programming procedure that runs in polynomial time. So you can now compute the distribution over configurations given your belief over the models in polynomial. Okay. All right. So, fine, we have done all this. So we now have a DTDE with belief update, but there is one key limitation still, which is that we still require models of the other agents. And this requires and this has to be a predefined model set. So you basically need to know, what kind of models the other agent, or at least you need to have a candidate set of models. And anytime you have to come up with a model set, you have to deal with issues like the absolute continuity condition, which I don't want to go into in this talk, but I can talk about it a bit more. But basically it involves knowing that, whether you're modeling the other agent correctly in your candidate set or not. So that issue is still there. And also the bigger issue is really that the belief update procedure needs to be done for every other agent. Okay, so we still have that growth in terms of the number of agents. It's a linear growth. It's not an exponential growth, but it's still there. And so can we do something about it? And so the question that we ask next is, can the agent population be directly modeled? So can we model it as a population rather than individual agents and then, as configurations? So here we sort of leaned onto the Dirichlet-multinomial distribution, which is a really well-known distribution that, allows you to model categorical variables. So this is the compound distribution where the Dirichlet is the prior and the observation model is a multinomial. Okay, so it basically looks like this for different values of the parameters alpha. So here, this is the this is the two simplex, basically a 2D simplex, and there are 3 parameters here. And so what we are going to do now is take the action configuration that we just saw, and basically it can be thought of as a set of samples drawn from the Dirichlet distribution. So we're going to model the entire agent population as a single virtual agent with, basically, for 4 agents, there are 4 actions, but as a single virtual agent. And then you can think of the action configuration as a samples drawn from this distribution. If you have been doing work in mean field systems, like how you have been doing, Sriram, I think this is not new. They have been using binomial distributions and so on. So this work is really not that. So, but what's new is that we actually show how you can update the Dirichlet distribution at each time step using private observations. Okay, so that's something that's new. So we actually show how you can start with the Dirichlet-multinomial distribution and then update it as the agents receive private observations. So here's that procedure. In the interest of time, I don't want to go through all the steps, but basically we show how you can start with a Dirichlet distribution and then end with a Dirichlet distribution after the update as well. Now, this is an approximation, but it's not a bad approximation. So we continue to remain in the space of Dirichlet-multinomial distributions even after the updates. Okay, quick run through the architecture of the agent now. So now we have replaced, we have a belief filter with configurations. So here's a procedure that, basically does the dynamic programming and gives you a distribution over the configurations. Okay. So here's a belief update over the models. And basically these configurations are then used in calculating the Q values and the V values. It basically is used in calculating the advantage function. Okay. And with the Dirichlet-multinomial distribution, we can further simplify the architecture. So we can just replace that whole belief filter, the belief filter operations with just the Dirichlet-multinomial model and just update this. So, it's a much simpler architecture, but obviously it is an approximation. Okay, and we continue to remain in the actor-critic schema. Okay, so send off private observations, update the configuration, send an updated configuration again to calculate the Q and the V values. All right, so that's basically the approach. That's a new multi-agent reinforcement learning technique. It's a decentralized training, decentralized execution, and it also allows you to scale to large agent populations. So now I'm just going to quickly run through some results on the org domain that I just also talked about. And hopefully, this will give us some peek into how well this approach works. Okay, so the first and foremost, what if you did not consider the history-dependent rewards? Okay, so you basically select a neural net architecture that does not consider the history-dependent rewards. One way to consider the history-dependent rewards is to use LSTMs, because they allow you to memorize past rewards. If you do not want to consider history-dependent rewards, maybe you can just use CNNs. So we use a version of the method that essentially does not explicitly model the history-dependent rewards. We remove SR, we remove SR, and then see whether the neural net architecture can help us here. And here you can see that, yes, the LSTM is able to converge to the optimal policy, while the CNN is not able to do that. Okay. So basically, this experiment shows that considering history-dependent rewards, so the bonus, is required if you want to reach optimality. In other words, the employees can get a higher reward by considering, by modeling figuring out a way to consider the bonus in their decision making. Next question. In the org domain, is cooperation really needed? Is it desirable in the org domain? And so here we basically compare an independent actor critic with IA to C. Independent actor critics are just decoupled agents. So there is really no cooperation or coordination going on. And here we show that, both IA to C plus, so where the bonus is part of the state space, they are able to learn the optimal policy, and IA to C plus, where the bonus is part of the state space, converges faster. Right? So, at a high level, this experiment shows that cooperation is needed to reach optimality in org. If you just have a bunch of agents working individually, decoupled completely, you can do better than that. Okay. Next experiment. How about extant mal techniques? So how about existing mal techniques? Are they applicable and are they feasible? So here we take two existing mal techniques, COMA and MapDDPG, and our result shows that yes, they do remain applicable. They do converge to optimal policy, but they require almost twice as many episodes as IA to C. And one of the reasons why is the partial observability of the actions of the other agent. Because the way those, these are both CTDE techniques, and the way they model, the other agent is basically assuming perfect observability. So when you introduce partial observability, they require way more training to be able to converge to the optimal place. Okay, so experiment shows that existing mal techniques are applicable, but they're significantly impeded if the other agent's actions cannot be observed perfectly. So if you have a real world domain where this is the case, you may still want to use them, but just know that they may not work so well. Next, what is the impact of the private observation noise? And here we show that, the private observation noise impacts different methods differently. So for example, you can see that, it impacts COMA and MADDPG much sooner. You can see that their performance starts dropping much sooner compared to the interactive advantage actively. Okay. And again, it is along expected lines, right? If you're not explicitly managing noise, if you are kind of ignoring the noise and you're just letting the neural network deal with the noise, yeah, then, it's not able to deal so well with it. It can deal with it, but not as well as if you're explicitly thinking about the noise. So it's along expected lines. In this experiment, we basically compare between using the belief filtering versus Dirichlet-multinomial. And here we discovered something really interesting. If you have less agents, then your belief update actually does better, So maintaining models and then doing a belief update over the models of each other agent actually does better for less agents, but as your population grows, the Dirichlet-multinomial approach works better. Okay, which again is I would say that is along expected lines, because as your population grows to thousands of agents, you really cannot, feasibly maintain models for every other agent and then try to update those models. Okay, so the Dirichlet-multinomial model scales quite well, and we have run experiments with up to 5,000 agents and is able to scale well to that. All right. So how about coordination across the different org structures? So, how about if the organization has different structures? And here we found that the cumulative rewards are higher in fully connected structures than other structures. Basically, in fully connected structures, there happens to be a lot more coordination and cooperation versus in tree structures or in star structures and so on. So this is basically a result that really is, at a macro level, that is kind of important to the organizational psychology folks or the management science folks. Okay, it is harder to coordinate across many small neighborhoods. And how about comparing with other many agent methods? So here we compare with some mean field techniques, and we basically show that, the mean field technique. So that's here, mean field, actor-critic, and QMix. They really were not able to converge within the time limit, while the interactive actor-critic methods were able to converge within the time limit. And between the two of them, the one that uses Dirichlet modeling learns much faster. Okay, so if you're wondering like why the mean field actor-critic, did not converge within the time limit, we can talk about it offline, but it has to do with the way you're constructing your mean field. Okay. All right, so that's the takeaway from this, that it basically shortens the amount of time that the belief update requires. Okay, so we are close to the end. So let me do a quick recap and then just conclude my talk. So IA2C plus essentially combines decentralized actor-critic based learning with a belief filter that maintains belief over a finite set of models of the other agent. Okay, so it does not require policy exchanging or action exchanging among the agents. It does not require perfect observation of the other agent's actions. It does converge faster than existing CTDE techniques that basically assume perfect observability of the actions. Then we also introduced IA2C++, which is basically IA2C that allows you to scale to larger environments, like the larger org domains. And here we showed scalability to up to 5,000 agents. And we have run some experiments with even more agents as well. And one of the reasons how it shows scalability is because it really, very efficiently models the agent population. Okay. So I'm just going to leave you with a picture of the University of Georgia. So this is the top view. I'm hoping to entice you to come there and basically let me reciprocate the hospitality that Pascal has shown, so well to me. All right. So thank you very much, and I'm open to questions. Okay. Should I take the Zoom question? I mean, are there any questions on Zoom first or the? Okay. Go ahead, Pascal.
Actually, there is one question.
Okay.
But I'll talk to that question. I guess the question is, when talking about balance, there is no mention to the extent to which there is a balance. We look like the individual does something for themselves in the short term, but later on you might realize they actually took the balance. So took the balance action where they were thinking of developing skills that could help the organization in the future. How do you account for this? Because you mentioned sort of the action perfectly when you use either the CD control scheme or for the individual agent specific controllers control scheme.
Okay, I believe I understand the question. So the question is, what is the distinction between the explicit balance action that we have and taking a series of actions where the first few actions are self and then the remaining actions are group? So in that way also, you're trying to achieve a balance, right? And so the key difference between the two is that balance tries to balance the two at every time step. Okay, so balance is actually an action that balances your interests between yourself and group at every time step. Whereas in the latter approach, you're first doing a bunch of selves and then a bunch of groups, which may ultimately have the same impact as doing a bunch of balances. Okay. So, but there is a distinction, between the two, in the sense that balance is at every time step. Yeah.
So, okay, so when you explain the configuration and counting, I guess, how many actions, to me, initially, it sounded a lot similar to the field approach.
Yes.
With the exception that now you actually know how many agents there are. So the new field approach.
Correct.
A distribution. So is that really the main distinction?
Yes.
Or is there more to it than that?
No, that is the only distinction. So you can easily convert an action configuration into the mean field by just dividing it by the number of agents. So it is analogous.
So then at the end, when you obtain key results, while the new field approach did not, does that mean that it was really the count here on the agent that needed is different? Or
No, I think it was more to do with the way that particular method constructs the mean field. So it's not about the use of mean field per se. It's about how the method, it's not about mean field per se. It's about how the method constructs the mean field of agents. So that is the reason why it does not do so well.
But I thought mean fields are constructed by essentially also just creating a configuration.
No, so here.
analysis on that. So I think that's why.
No, that's fine. So I think that so what Sriram is saying is that noise is also a factor in why the mean field actor-critic did not do so well. So yes, noise is a factor, but it also that result is particular to the way MFAC uses mean fields. Okay, so it may not align with your expectation of how mean fields are used, can be used in an approach. Okay, so that result is particular to that method. I wouldn't read it too generally for any mean field approach. Okay. Also, if you look at the mean field approach, the way they applied it, make an approximation in terms of the neighborhoods, and I think that's one of the reasons why. Yes. In the decentralized, yeah, each agent has its own critic and actor. No. Which chart are you talking about? Okay, the value is yes. Yes, that's the agent's cumulative reward. Yeah, it's from the agent's perspective. Yes, it's not for the whole organization. Yeah. Hmm. Yes, so I think that is definitely playing a role here because in structures where they basically divide the agents, the employees into units. Yes, you are just considering focusing on that small unit, and so you're not taking into account the whole configuration of the organization. Yes. Correct. So the group reward is based only on its own neighborhood. And it's only modeling its own unit. Yes. Yes. Right. Correct. Because you still need to ultimately the organization has all the employees. Correct. Yeah. Okay, hold on. I think he has his hands raised since a long time, so I don't need it.
So yeah, so this is proven from her.
Okay, so in terms of theoretical proof, we don't have an explicit proof, but because we have an underlying model that is the interactive POMDP, we did not feel the need to show the proof of convergence because the interactive POMDP is converged to optimality. So there is an underlying proof for the model that it converges to optimality.
So assuming that it converges,
and so far we have always seen convergence. So maybe that's a bit anecdotal, but we did not quite feel the need to theoretically show a proof of convergence.
Now, do you take a couple of approximation steps, right? Especially like, for example, focusing on Dirichlet.
Yes.
For example. Do you have any sense of how much you lose on global optimality for those?
That's a great question. And okay. So the question is sort of two-part question. I think part one was, is there a proof of convergence for interactive A to C? And the second question is, when you model the population using Dirichlet-multinomial, do you have a sense of the approximation loss? Great question. So, first of all, organization domain is not the only domain on which we have explored. If you look at the paper, there are other domains as well. And in all of those experiments, we haven't yet come across a situation where we haven't converged to optimality with the Dirichlet-multinomial. However, this is an approximation. So I'm sure that there may be a way to quantify that loss. Okay, but also keep in mind that we are looking at populations that follow those two assumptions: action anonymity, population homogeneity. Moment you have populations that do not follow these assumptions, these techniques may not be applicable.
So when you're talking about convergence or optimal solutions, I assume that we're talking about local optimal, or maybe in that particular class of policies, right? We're not talking about global. Probably even evaluate
yeah.
what that might be in a global sense.
Yeah, I think that's a good direction. Also, when I was talking about the proof of convergence, I was plainly talking about IA to C plus. So the vanilla IA to C, not IA to C plus plus. So we already know that the Dirichlet multinomial is an approximation, right? As you update it, we are approximating the distribution to be Dirichlet's.
Now, just lastly, wondering, is there a way to have simpler models, like efficiency models for modeling other agents?
Yeah. I mean, so fictitious play is always an interesting baseline to apply, right? Because basically it just says that, okay, model the other one as a bunch of probability distributions. But I think it has been shown many, many times that the reason why it is called fictitious play is because that's not how agents are playing. So anybody is most welcome to use fictitious play as a baseline, but I really doubt that in these kinds of sophisticated domains, is actually going to do that.
I need to have collaborative agencies whose timing is shown.
Yeah.
To convert,
right. And also, fictitious play. Yeah, I mean, it does not quite model the other agent as following a policy. It models the other agent as following a distribution that is constantly changing. So where behavior involves knowing your prior history and then acting according to that, I mean, it's hard to see how it applies. But I'm always a proponent of using FP as a baseline, because then you just get sort of a more advanced null hypotheses out of the way. So I always use it as a baseline. Yeah.
So in this graph over here, I think you said QMix is a mean field technique, right?
No, MFAC is a mean field technique.
So
not
is not a
QMix is not a mean field technique.
So QMix actually is for deck boundary, right?
Correct.
So how did you apply this to a mixed setting?
Well, so basically, so deck boundaries assume a common reward. We just separated the reward, essentially.
Okay.
So we just sort of instead of having a common reward, because our setting does not have a common reward, we just separated the reward and we were still able to apply QMix. So, if you want to know the exact details of how we apply the QMix, I would connect you with my doctoral student.
Okay. So is it something like you add all the rewards of all the agents and make it like a single?
Correct.
To give everybody? Okay, but
similar. I'm not sure. I don't want to. I would look at the paper and see how it is done.
Because I want to know, because if you change the reward, the values will be different. And if you do some shaping, the values will be different. Then how could you actually kind of how could you make a fair comparison?
Correct. So we did take a lot of steps to make sure it is a fair comparison. Okay, you're right. And so I think that one way to apply sort of these a common a technique like that applies only cooperative settings to these kinds of approaches is to just combine everybody's reward together and then just send that to every other agent.
Yes, but then the comparison across values is because
okay, yeah.
The reward that agent A gets is not the same.
It's not the same, yes, right. Correct. Correct. So I think I probably need to get into the details of how we applied QMix. Yeah. Okay. But QMix, yeah, I mean the underlying model for a QMix is a deck boundary P, you're right. But maybe I'll have to refresh myself on QMix, but maybe it can be applied to, so many of these MAL techniques, they still apply to competitive settings. Like they show results on competitive settings.
Yeah, so instead of QMX, I was wondering why you didn't use something like DBT, because like, you can choose.
We have done MEDDPG. Yeah, MEDDPG is another one of the technique that works on cooperative and competitive settings.
So I was thinking you were looking at mix.
So I think in our earlier paper, we used MEDDPG and it quickly sort of fell out as a good competitor. So then we moved on to more recent techniques, and QMix was a more recent technique.
Okay, and then in general, like this is a very new type of graph. Like I've never seen like time being used in this.
Correct.
So I'm kind of very confused by that, because I know there are 4 different implementations of MSAT, and each will take like more time or less time than the other. So it is like heavily dependent on the implementation.
Right.
So like, like I admit that you actually want to show that something can be better.
Yeah.
But then how do you actually, make such a plot like without going into the implementation?
Well, so yeah, I think that, it's a good point. This chart is a bit different because normally you have the number of episodes on the x-axis. So there's a really strong reason why we're not using the number of episodes, because the episodes in different methods are different. Okay. The definition of episodes in different methods is different. So here we are basically using time as your independent variable. So in the sense that we are saying that, okay, here you have a fixed amount of time. What can you do in this time? Ultimately, when you talk about applying techniques, it's about the amount of time the technique is taking. Sure, this scale may be different if you use it on a supercomputer versus your workstation, but as long as you, test all methods on the same computing platform, you can generate this chart. So the question you're asking is, in this amount of time, how much can you do?
So like it also depends on the implementation,
Yeah.
So
sure. I mean, yeah, you can try and optimize your implementation. I think here we have taken an existing implementation that we've thought was the best among the different implementations. Sure, you can try and optimize it, but then you can pretty much optimize anything, right? It's giving you a general idea of how well they are doing.
But this order problem, so the action is so simple. What if you make them a little more detailed?
Yeah.
People do that. It's not just
yes.
Like creating something that communicating. What types of things people do with things like I know that might go around.
Correct. So the question is, the org domain is somewhat simplistic in terms of the number of actions. Can we try and model more expressive actions? And so we actually started by having more expressive actions in consultation with our collaborators, but then we realized that, okay, computationally modeling this is not going to be easy. And so we sort of just try to abstract the actions. But I'm with you that, if you truly want to model an organization, it's more than just, these choices that you are facing. But ultimately, we are also interested in modeling the tension between cooperation and competition. And that's why our actions are focused on self, group, and so on.
So
what is the reward function for the self action? So the reward function for the self action depends only on the agent's own action, whereas the reward for the group depends on the actions of all the agents in the neighborhood. I'm sorry, I cannot hear you. You mean the exact values? Yeah, it's a table. If you want the exact values, then yeah, we have it in the paper. So yeah, I think it should be in the appendix of the paper, but yeah, we do have the exact values. And so all the code for all of this, oh, by the way, I think I did not show the publication, so that's my mistake. So let me quickly show the publications so that you can access them, and the code is fully available. Whoops. Okay, sorry, I just stopped the screen sharing by mistake, but anyway. So the code is fully available. Here are the publications, and the code for each one of these is available. And we have also published the org domain. So you can also, yeah. I think I'm kind of done, so. Oh, okay. So yeah, you can definitely access the org domain. I think there's another message on chat. Oh, it's just you. Okay. Okay, so let me, I think it's this. All right, so yeah. Okay, so yeah, these are the papers. And so if you're interested in the public and private observation, please refer to the top paper. And then if you're interested in the IA2C techniques, then we have the remaining two papers. All right, any more questions?
So, there was the slide, I think it's slide 25 and 26, where you showed like the transition functions, the queue functions, and all of that for the joint action and
Correct.
the configuration. So, you had like an exact equivalence in all of those, I think you had an exact equivalence. Yeah, actually, is this, I think, the equal, especially the queue.
No, it is exactly equivalent under the assumptions.
Is it exactly equal or is it like an approximate?
It is an exact equivalence under the assumptions.
Because for the mean field case, you can actually show that it is an approximation. It's not-
Well, the reason why it is an approximation in the mean field is because they just focus on the neighbors of the agents.
but
So the way they do the approximation is that they just focus on the neighbor of the agents and not all the agents. Here we are focusing on all the
No,
agents.
so this approximation for the mean field case is an approximation. on
Yes,
the-
I know what you're talking about. I have the proof in my memory. I remember what you're talking about. But here, no, under the assumptions, you can replace the joint action with the configuration. And the reason why is because under the assumption of action anonymity and population homogeneity, you can apply the delta function to it and arrive at the configuration. So there is no approximation here. Okay. And if there is no approximation here, then your Q function is ultimately A is a function of these, right? It is an equation